Okay, great. So I want to thank you all for joining me today. This is part of a series of webinars that we plan to present monthly to try to bring people or familiarize people with some of the features of TreeAge Pro that they may not be aware of, or if they're aware of them, they may not have much experience with them. Now, this isn't going to be a full training course where we spend a very long time. We should be done within half an hour, but it's more an introduction to the techniques involved so that you know that you can do them, and if you really need to do them for a project, you can ask questions through support, and if you really need more help than that, you can get some short-term consulting time with us to help you with the model. Overall, our webinar series is available on our website under training and then TreeAge Pro webinars, and you see, just fill out this form to register for one of them, and we'll be sure to, obviously you know this because you've done this before, we'll be sure to make sure we invite you to the next webinar. Now, let's get back to the topic of this one. I'm muting everyone's microphones, but please feel free to use the chat window in the GoToMeeting control panel to submit questions, which I'll try to take at reasonable breaking points within the presentation. So, without further ado, let's talk about infectious disease models. Now, infectious disease models really differ significantly from a typical TreeAge Pro model in three ways. Starting with a traditional TreeAge Pro model, it typically will have multiple treatments, and you're comparing treatments, and what you're really looking for is the average cost and average effectiveness, some kind of health outcome, to use those to generate ICERs and compare strategies. With an infectious disease model, there are some significant differences there. The first being, you probably don't want to look at an average cost and average effectiveness per patient. You probably want to look at more population dynamics. So we're not going to have a cohort of size 1. We're going to have a cohort of the size of the population that could be affected by this infectious disease model. So that's the first significant difference. The second one is we need to be able to add people to the model. There's going to be new people that become infected or become susceptible to infection. So not only is a cohort going to start with a size that's not 1, we're going to dynamically change it with time. And then the third thing is that we want to be able to use the components or the membership in the states to have an impact on the likelihood of infection. So specifically, we'll get into the more details. This infection probability here is going to be affected by the way the cohort is right now, the health status of the cohort in general. So you maybe have never created a model where an individual's experience within the model is actually affected by the other people in the model, and that makes the model, one level more complicated than your typical model. So that's just a kind of a summary of what we're going to do, and now we can get into more of the details. So, what's an infectious disease model? So, it's a pandemic, whether that's a flu or SARS or something like that, some kind of issue where we're worried about infection spreading through the population. And the membership within the states becomes very important. And we're going to, the model we're specifically looking at is this one right here. Dynamic Cohort Infectious Disease. It comes with your software. So you're not going to have this downloads, that's mine, but you're going to have example models here in the projects view. If you don't see the projects view, you can always open it from here, view projects. And then example models, healthcare, and we scroll down, and we're specifically looking at this model. So if you have updated to the most recent software, these two dynamic cohort models were added with that. So if you don't see this, you probably need to update your software and refresh the example models within the context of the software. And if you have any trouble with that, please feel free to contact me through support@treeage.com sometime after this the conclusion of this seminar. So that's the model we're going to look at. And now let's look at some of the things that are unique about this model. The first thing to look at is the cohort size. Now, typically for a regular Markov model, these would all be fractions. Let's ignore this one to start. These would all be fractions. So you might have, a prevalence here, everyone else here, nobody immune, and dead here, but they'd all be fractions of 1, so that you have a cohort of size 1. In this case, we don't have that. If we look at these initial variable values, I'm going to hide this for now to give us more space. But if we look at the variable properties for those initial variables, I'm using the filter here to only look at the variables that match this. You see we're starting with 10 people infected, and the total population is 1,000, and everyone else is going to be uninfected in this particular example. So we'll have 10 people here, 990 people here, and nobody in these two states, and that will be our starting point. Now, how do you do that? Well, most models will give you an error if you enter values at either a Markov node or branches of the Markov node or a chance node. If you enter values that don't sum to 1, TreeAge Pro will, by default, throw an error. And it should, because most of your models, you do want those probabilities to be coherent. But this is an exception to that. So what we allow you to do, and you'll see this little red flag here saying that I've already done it, but when you right-click on either a Markov node or a chance node, you'll see change coherence, and you see that this one's already set to allow probabilities to not sum to 100%. So this particular node within the context of the model has been allowed has been freed from the restriction to be summed to 100%. So I'm able to enter counts of people here rather than fractions. That is also true here, where I'm going to use this to add new people. And this, I believe this is about 10 people. The numbers don't necessarily matter that much, but the concept is the same, that this node right here also has coherence set to not be 100%, so that I can add another count of people here rather than a fraction of a person. So you never want to do this for your whole model, although there is a way to do that through tree preferences. You really want to allow it only at specific nodes where that makes sense. And that's where the non-coherence comes in at specific nodes to allow the cohort to expand beyond fractions of 1. So that's the first thing. The second thing is in this model that's kind of unique to things you haven't done before is this entry node. You see this arrow here. So this entry node was added in TreeAge Pro 2018 to allow you to add new people to the cohort, but not have TreeAge Pro think this is a real state. So this add new people will be executed every cycle. And in this case, we're going to add new uninfected people in, although I could add people to any states if I wanted to. But the key to the new feature is it's not considered a state, so you don't get the slight miscounts in the model where this is considered to be a person that's up here. Where I used to have this be a chance node with a 1 before 2018, so you always had your cohort slightly off because you had this fake person being used to add people into the model. And so now you have the capability to use an entry node, and you see it over here if I wanted to add it, entry node to facilitate the addition to your cohort without having TreeAge Pro interpret that as being an actual health state. So it's a pseudo health state specifically being used to add new people into the model. Okay, so that's the second thing. Now the third thing is the effect that the overall cohort has on probabilities in the model, specifically probabilities, but it could be on anything. And that really comes down to the details behind this probability of infection. So I want to look a little bit at the probabilities, the variables that comprise that, so that you can see how this would be done. So I'm going to show my variables again, and I'm going to start by just looking at the prob infect right here. And if we look at probability of infection, first, starting with the rate to prob, this just converts a rate to a probability. And this 1 over cycles per year has to do with what's the time period for this transition probability. I'm not really too concerned with the cycles per year right now. I really want to focus in here. So this is a rate. This would be some kind of parameter, right, that is related to the disease, how fast that disease progresses. So different diseases would have different rates. But this proportion infected what we're doing here is that's calculating the proportion of the overall cohort that's alive that is infected. So if, let's say you had 10 people infected, 10 people not in or susceptible but not dead, and 10 people recovered and immune, that would be 30 total people alive, 10 of whom would be infected. This proportion would be 1/3, and that 1/3 would contribute to the probability that affects your probability of infection. So in essence, what we're trying to do is what we've done here is tie this probability of infection to the membership in these three states, specifically the percentage of infected relative to all of the alive states. Now, we need to look a little deeper, because you don't need to necessarily believe that prob infect is ready to go as is. So specifically, how did we get this proportion infected? That's the next thing we want to look at. So if I use this filter again and look at proportion infected, now we can see a little bit more details into this. And you see what we've got: two more variables: count infected, count alive, divided by count alive. Now, count infected needs to be the percentage of people in this state. Count alive needs to be the sum of the people in all three of these states. So let's see how we reach that point. So I'm going to clear this and look at the count variables. And you see this state prob command here. Now, this function has been in software for a very long time, but not very many people know about it or use it. And what state prob does is it returns the percentage, or in this case, the count of people in the states. And the index 2, 3, and 4 just counts down from the top. So uninfected, this is 1, here's 2. So this state prob 2 is going to return the count of people in the uninfected state. State prob 3, count infected, is going to return the count of people in the infected state. And state prob 4 is going to give back the count of people in the recovered immune state. And the sum of the three of those is the count alive. So if we went back to the proportion, it was this count infected, how many people are in this state, divided by the sum of the people in all three of these states. So now we have the proportion of people of the non-dead people who are alive people. Excuse me, I said that wrong. The proportion of people who are infected relative to the proportion of the number of people who are actually alive. And that informs this probability. Now, it may seem a little bit complex, because it was 2 or 3 variables deep, but that's because when we build models, we like to break down complex calculations into a series of smaller calculations, each of which is much simpler. So we start with the counts, then we get the total count, then we bring that into the proportion infected, and then finally we end up with the probability of infection by moving in smaller steps to achieve something that's more complicated. Now, that really is all the elements of the model that are unique to this kind of model. I'm just going to check to see if there's any questions in the chat window. I don't see any yet, so I'm going to continue forward by actually analyzing this model. Okay, so what I want to do to analyze this model is I only have one strategy, so I'm not going to worry about decision analysis, cost effectiveness analysis. What I really just want to do is look at this infectious disease portion of the Markov model and see how it's calculated. And I'm going to do that by selecting the Markov node and then choosing this option in the analyze perspective to run the verbose extended Markov cohort report. And so now we can see the fruits of the efforts that went into that model. Specifically, these are not proportions of 1, right? Like I said, I'm starting with 10 infected people. There was a total population of 1,000. That means everyone else was uninfected at the beginning. Now, obviously, that's going to change as infections develop and people recover. So the flow is very similar to what you've seen in a typical model. But what's particular to this model is the counts here, that they're counts and not fractions. The second thing that we looked at was the addition of new people. That's happening here, right? Notice there's no cohort here because it's not a real state, but we are adding new infected people based on a rate of a birth rate, which I didn't show you earlier, but it's a birth rate based on the alive count. So this number came from birth rate. And where did they go? Well, they're going to go into the uninfected. So let's make sure that works. So we take the uninfected. This 976 people. Now you'll see fractional people because cohort analysis is done based on probabilities. So, obviously there are no real fractional people in the world, but when you do this kind of analysis, you will see fractional people. So of the 990 who started uninfected, 976 remained uninfected. We got approximately 7 new people. And so when we go down to stage 1, we have 976 plus 7, 983 people. So this is showing you that we have the counts, and this part is showing you that we added new people into the cohort, and that happens every cycle. Right now, we're adding a different number of people because we're using a rate based on who's already in the cohort. But in essence, that's going to be executed every cycle. It would be possible to not execute this by making a logic node or something here before you add people to say, I only want to add people for the first 10 years or whatever that is. So you could have more control than we've elected to put in this model. But in this model, we're using a rate times a rate applied to the people who are alive, and that becomes the new people born into the model. Now, meanwhile, there will be people dying off. So the people will be added to the cohort up here, and they will be dying, which will then change the cohort size, because some people are dying as other people are living. Now, someone asked me to make them presenter. I really can't do that right now, but if you want to follow up after the presentation, we could look at your computer at a future time. But I need to move forward with the whole group for now. Any other questions before we move forward? Okay, so let's look a little bit deeper at these results. And yes, there's cost and stuff being accumulated, but that's not really the point of what we're doing here. We're accumulating costs for the infected people. We really are focusing more on the flows. But the accumulation of cost and utility, et cetera, would be the same as any other model, except that it's multiplied times cohort counts rather than cohort percentages. Now, the summary report, that would just kind of give you the same data from the cohort report, but in a two-dimensional grid. If you wanted to dump this to Excel, or you wanted to get a count of cost for budget impact reasons, this would be a good option for that. Because exporting this to Excel is messy with all the groupings. But if you simplify the report into a two-dimensional grid, that's a much easier one to deal with post-export. And then what I really want to look at here is the state prob. And this is showing you graphically the flow of patients in the model. So you can see I start with uninfected, that goes down as people become infected and eventually immune. Then it goes up as you have people, new cases developing faster than people are recovering from them, and it starts to stabilize eventually. Now, I can't say that every model like this would stabilize, but this one kind of does. Whereas other states are behaving differently. So the infected, for example, goes up as the infections are happening faster, then goes down as people recovering faster. And it happens to stabilize as well. Meanwhile, the immune, it has also gone up and kind of stabilizes at a fairly high number. Now, dead is clearly rising with time. Now, we ran this for a very long time period, so that's why you're seeing a lot of dead. So we had new people coming in and people dying off, so the dead is increasing. So this state prob graph is showing you the counts in the states. Now, in a typical model, they'd be fractions, but not in this one, obviously, because we have a larger cohort size. But this can be quite illuminating in terms of what's happening to your cohort as this potential infectious disease outbreak continues into the future. Okay, that's most of what I was going to do for the main model, and now I'm going to show you what you'd have to do if we were going to run it as a individual patient simulation model, because this same kind of modeling technique can be done with individual patients. Now, there's no reason that we would need to run individual patients through this specific model, because in essence, we have no elements of the model that require patient level data, like heterogeneity, for example, or some kind of scenario where becoming immune was not as simple as just moving this way. Maybe you could have the disease twice before you become immune. If you had some kind of scenario where we needed either heterogeneity or event tracking, where patient data became critical, then we'd want to run patients through the model rather than a cohort analysis. Now, to run the patients through the model takes a very long time. And so I'm not going to run it right now because we'd be sitting here waiting for the results. Why would it take a long time? Well, we have a lot of patients. We have new patients coming in through every year. We've got to process all those patients, and we have to process all those patients at the same time, right? We wouldn't be able to just run one patient to the end because we would lose the ability for this probability of infection to be based on the status of the rest of the cohort. So when you run microsimulation on a model like this, which we're not going to run, but I'm going to show you what you did if we were going to run it, you would, first of all, you'd want this set to sum, right? Because we were looking at summary of the data. We don't want average. But secondly, you notice you don't have the option to change the number of patients because this isn't controlling the patients. These non-standard, non-coherent counts are controlling the patients. So we're running one pseudo patient here because we know this is going to be 10 and 990 here, plus new patients coming in here. So we don't specifically run the number of people because the number of people is handled within the model, within the pseudo probabilities within the model. The other thing we would need to do is we'd need to run parallel, and you notice that you have to. Again, that's very much associated with this probability of infection, and we would need to actually, we need to have them running in a synchronized manner with time in order for this probability of infection to accurately be based on the membership in these states. So those are the things that would run differently if we were running a microsimulation. Now, I saw a couple of questions come up, so let me try to address those. The first one was, how do you address heterogeneity among different subgroups? There are a couple of things to do, but typically what people do is they will assign characteristics to individuals as they enter the model. And that can be done via distributions. So you could have a distribution that assigned gender, let's say, to each person, or assigned age to each person, et cetera, et cetera. That's typically what people do to assign those characteristics. Another way to do it is through bootstrapping. So if you have individual patient data that you know, like real patients, you can assign the characteristics of our simulated patients with the characteristics that actually existed in real patients that you've seen in real life. So those are two ways to assign characteristics. Now, you wouldn't do that unless you were going to use those characteristics as part of the movement through the model. So let's say if the probability of infection was different, both based on these percentages, but also based on gender, then you'd want gender in the model, and you would use that to make this probability a little bit more complicated. I know David had a question on social contract structure. I'm not sure. I don't really understand that question, so I can't really address it. So maybe we could take that one offline and discuss that after the presentation. So now I know I can't run this because it will take too long, but what I have done is I've run it in advance. So I'm just going to open up this, and just opening the results takes a little while because there's so much data, although that was nice and fast. One thing I did forget to say is that if I were going to run the patient simulation and I wanted to get those cohort level details, I would also want to be setting time reporting on. So I would enable time reporting, and I would record the payoffs. There are no distributions of trackers in this model. And what this would do is basically record each patient at every node. First of all, what node they were at, and secondly, how did that affect the accumulation of value in the cost and effectiveness payoffs, and any trackers you could include in this as well. So time reporting allows you to see what each individual happens to them, like what movements they went. Did they go to this node and then this node and then this node? And not just that, but what happened to the data how did they accumulate cost as they move through that? Now, that's really why the model takes so long to run, because it's storing an enormous amount of data. Every patient, every node, every impact on every value. So it takes a lot of data. So your result set is very large, and it takes time to generate it. But this is the pre-run results. I'm not really worried about this. I'm not going to do decision analysis, but I do want to show you that we can get the same look of cohort report from the individual patients that we got from the cohort analysis. Now, when you run cohort analysis, it's natural. That's the way it's analyzed. That's the way the data is generated. But with the individual patient simulation, what we're basically doing is taking that huge amount of data and reconstructing the cohort analysis output based on what happened to the individual patients. And that's why it takes some time, because it's literally taking hundreds of thousands of data records and combining them back into one report. So we'll just have to wait for that to finish. Oh, and there it is. Okay. Notice the same thing. 990 patients uninfected, 10 infected, just like before. You notice all of these are now round numbers, right? They're not fractions, because they're now people. They're now individuals being sent through the model. So you're going to see these as non-fractional value, because you can't have half of a simulated patient. But everything else in here is basically the same as what you saw before. So I'm basically I'm trying to show you that you could run individuals through this model, even though we didn't run it real time, and even though we didn't really need to for this model, because there was no patient characteristics that affected any kind of cost, effectiveness, or probability. But you can if there were those elements, and those were critical to the model. And again, we could run the state prob from that. And the results aren't exactly the same, because there's going to be some noise with a cohort size that's only 1,000. It's not that big to get perfection the way you get with a cohort analysis, but you see the same trends, right? Stability with time, dead going up, etc. So I just want to make the point that you can run basically any Markov model with microsimulation. So when it comes time and you say, oh, I've got a piece of data that's critical to patients and I need that, you don't have to rebuild the model. You just integrate that element into the model and run it a different way. So I think that brings me to the end of everything that I wanted to talk about today. I'm going to take any more questions that have come up. Any other questions before we finish? Please feel free to contact us in the future with any questions that you may have. And I hope that you're able to join us for another webinar sometime in the future, as we try to address more and more things that we'd like to see people use in the software. We will be doing one specifically going through these kinds of reports. That's the next one. And eventually we're going to do another one on dynamic trials, or running trials in a parallel manner that takes advantage of that through resource constraints. So anyway, that's all I have for today. Thank you all for joining me. Wish you the best in the future, and maybe we'll see you again for a webinar sometime in the near future. Thank you.